Okay, so let's continue our discussion from our last time, where we talk about the normalization. Normalization is where we stopped. So recall, oops, like how can I enlarge this window? So recall that what we have been doing so far is to discuss the gene expression count data analysis. And we first talk about differential expression analysis, which is to compare one gene's expression levels between two conditions. And we said that that is under the assumption that the measurements, these two sets of measurements are comparable, which means that they are in the same unit. So it makes sense to compare them. But this is questionable if they are measured in two batches. So we need to account for possible batch effects that makes those two sets of measurements uncomparable. So to address that, normalization or batch effect removal, these two terms are actually used exchangeably in many times, are used to correct the data. So we will perform differential expression analysis after the correction. And we talk about three ways to do the normalization. The simplest one is to simply normalize by the total sequencing depth or the library size. So we basically make sure that for each sample, we take the sum of the gene counts in that sample, then the sum must be the same for all samples. So that's the basic assumption. But we said that this assumption, if you want to treat the corrected gene expression values as the absolute expression levels, then this assumption assumes that all the samples have the same total amount of transcriptional activities. And if this doesn't hold, for example, some samples may be from a pretty silent state, while other samples are from a very active state. If that's the case, then what we can do here after this normalization is that we can only talk about the relative expression of a gene in relation to other genes in that sample. So we cannot talk about absolute expression levels. This is the thing we should pay attention to. Okay, so if you don't believe that this is what you want, and you have additional information, say that you know some genes, which we can call as housekeeping genes, have constant expression across all samples. If you know those genes, you can just normalize your sequencing counts by those genes. So basically, what we're doing here is that you're not going to make the sum of all genes equal across samples. Instead, you're just going to make the sum of the subset of housekeeping genes constant across all samples. But still, it's just a linear adjustment. You just do the division by a factor or multiply by a factor so that the count in a sample may be enlarged or reduced to match with the sum of other samples. So these two are simple, just doing a factor calculation. The third one is a little more complicated, but still it's very easy to understand intuitively. So quantile normalization basically means that you try to make the distribution of all genes. Let's say you have P genes, then you have P values in the sample. You want to draw the empirical distribution of those P values. So for example, like a histogram. So you will get one histogram per sample. And you want to make sure that the histogram looks the same for all samples. And that's the result we will get from this quantile normalization. So what is this assumption here? The assumption is that we try to make sure that every sample has the same distribution across all genes. Does that make sense to you? So last time we said that it only makes sense when you are assuming that the genes are basically the overall transcription distribution across all genes is unchanged. And you believe that only a small proportion of genes undergo changes, expression changes, and their changes will not alter the overall distribution of all genes. That's the assumption you're making here. So I would say it may make sense when you are dealing with replicates, right? In replicates, you believe that the overall distribution should be the same, but it may not always apply. For example, in the previous example, some samples from a silent state, some samples from an active state, then it doesn't make sense to assume that the overall distribution is the same between the two states. So that's the limitation of the quantile normalization. So I just want to make sure that we understand each kind of normalization method has its own assumption. You need to assume something is unchanged so you can normalize based on that unchanged status or unchanged thing. Otherwise, there's no way to do normalization. Hopefully this makes sense to everybody. Okay, so another type of normalization methods I'm going to talk about is based on what we call model-based. So basically the previous three types, based on sequencing depth, based on housekeeping genes, and based on quantile normalization, they don't assume a probabilistic model, right? So we don't call them model-based. But a more common or some more sophisticated way of doing the normalization is based on a probabilistic model. Since we are talking about count data, so a gene's measurements are counts. So I'm going to continue today by introducing the most commonly used count distribution. It is a probability distribution for constructing probabilistic models. And this is called the negative binomial distribution. Okay, so to introduce the negative binomial distribution, we will start from a simpler distribution called the Poisson distribution. We'll go from there. So let's start with Poisson. So how many of you here have heard of Poisson distribution? If you have, yeah, you can raise your hand and let me know. Okay, great. I will say many of you. Okay, great. But still, we have a few of you who didn't raise your hands. Then I think I will just do a quick introduction. The Poisson is the most common count distribution. So let's say that we have a random variable x, and we say this x follows a Poisson distribution. And this distribution only needs one parameter. We call lambda. Please note that here the lambda is positive, and the count values that x can take is non-negative integers up to infinity, theoretically. So basically, Poisson distribution gives you the probability that this x takes each possible integer value. So in particular, we know that the Poisson distribution has this very nice, we call probability mass function. Sorry, I should say small x, my bad. Small x. So that's the value for each small x it takes. We know its probability is actually lambda to the power of x and exponential to the negative lambda divided by x factorial. This is the Poisson probability mass function. So based on this formula, you could compute what is the probability the random variable takes value 0, 1, and 2, and so on. And what's special about this Poisson distribution is that the random variables mean and variance are only depending on lambda, the only parameter. So this is the most important property of this Poisson random variable. So the mean is equal to the variance equal to lambda. So in other words, lambda being larger will give you a larger expected value for your random variable. So you would expect your random variable to be more likely to take larger values. However, the variance also increases. So if you have a large lambda, then the x will have a wider spread around the mean lambda. So this is Poisson. But when we use Poisson to fit to our data to see if, let's say for a gene I, okay? So let's say if we have a gene I and we have n counts, then the question is, do the n counts follow a Poisson distribution? So by saying follow, we would say that let's summarize our n counts. So for example, we have how many counts being 0, how many counts being 1, how many being 2. We will compare those proportions to the probabilities we would expect from a Poisson distribution. And we will find the lambda value so that the Poisson probabilities best fit to the observed proportions of 0, 1, and 2, etc., etc. So that's what we'll do. However, what might happen is that even you try your best, find the corresponding lambda. And by the way, the way I described to find the lambda value is what we call the maximum likelihood estimation. Okay, so MLE stands for that. So even if you try the best to find the lambda value that can best explains your data, which means that that lambda value gives the largest likelihood value. And recall that we used that before, right? The likelihood of lambda is defined as the probability of observing your data given that lambda value. So if we pick the lambda value that can make the probability of our data the largest, that means this is the lambda value that can explain our data the best, then we may still find, it doesn't fit our data that well. So for example, what if I observe for my n counts that here from those n counts, if I call it just for simplicity, I call it y1 to yn, sorry, xi to xn, sorry. So then I can compute, this is what I call a sample, okay? A random sample x1 to xn. Let's say we compute the sample variance using this formula. Okay, this is the sample variance formula. And also the sample mean, which is defined as the average. So what if I observe that the sample variance is much bigger than the sample mean? And then this is contradicting with the fact that what I would expect from the Poisson distribution, because this sample variance is an estimate of the population variance lambda. And this sample mean is an estimate of the population mean lambda. So both are estimating lambda, but they are very different. So this is a strong indication that the Poisson might not be a good model, because we would expect them to be similar in scale if the Poisson holds. And this is what we call, this phenomenon is what we call overdispersion. So overdispersion is talking about a phenomenon that the variance is bigger than what you expect from a model. So if you're using Poisson, then you expect the variance to be equal to the mean. But from the data, the observed sample variance is much bigger than the sample mean. Then you call this overdispersion. So that's the simple way to explain what it means. So to address this issue, what we try to do is that we want to add some, I would say, some additional variance to our model, but we still want to keep the count model. So this gives us this idea, and this is a general idea in statistical modeling. If you think that using this Poisson model, the variance is not large enough, that is not what you observe from the data, what you can do is that you can add another layer of distribution for the parameter lambda. So instead of treating lambda as fixed, a single value, we allow lambda to vary. And then the variance of lambda would bring additional variance to X. That's the intuition. So we call this hierarchical model, and we just add a gamma distribution on top of Poisson. So we call this gamma Poisson model. And this model has two layers. The lambda parameter follows a gamma distribution. And we know the gamma distribution has two parameters that are both positive. We denote by alpha and beta. And also the gamma distribution has a support or domain on the positive real line. So therefore, when you sample from a gamma distribution, you would get a real positive real number, and we call that lambda. Okay, then given this lambda, we draw our X from Poisson lambda. So you see, this is why we call it a hierarchical model, because we first draw one random variable, conditional on that, we draw the second random variable. Okay, so in this case, how can we derive what we're still interested is the marginal distribution of x. In other words, what is the distribution of x regardless of lambda? So to do that, the probability mass function, we still write this big X random variable taking a small x non-negative integer. To do that, we are going to basically integrate out the middle, the first variable, which is lambda. So what we do here is that we would use this joint probability of x and lambda and integrate out lambda. Okay, this is what we'll do. So basically what we will do is this thing. So I'm actually a little bit abusive notation here. So this is a joint probability. So it's because x is discrete, lambda is continuous. I put them together. So this means that big X is taking this value, small x, and lambda can take any value. This one's continuous. It's about its density. And I do integration over lambda. And I let lambda go from 0 to positive infinity. So basically, I consider all possible values of lambda and jointly with x taking this value. Then I integrate our lambda. So it's like the integration can be considered as a sum, right? But here, because lambda has infinite number of values to take, we take this integration and it's continuous. So for this joint probability, we can use this hierarchical model to decompose it. We can write it as the probability of x takes value small x conditional on a particular value lambda times the density of that particular value of lambda, d lambda. Okay. And then this can be obtained from Poisson probability mass function. This can be obtained from the gamma density. Okay, so these two, we both have closed forms. Then what's left for us is integration. We want to solve this integration problem. But I'll leave that out. And what I can say is that, so with this formulation, then we can define this resulting distribution. So the distribution that follows this, taking this probability mass function, the distribution that has this probability mass function shown as PMF is called the negative binomial distribution. Okay, so this is the definition of the negative binomial. It can be defined as the Poisson gamma hierarchical model. And one thing we want to say is that for this distribution, negative binomial distribution is specified with two parameters. So we say that x follows NB with two parameters, and one parameter is called mu, one parameter called phi. Okay, this is the most common specification. So what it actually does is that mu is defined as the expectation. Okay. And I would say both mu and phi are positive. Okay, for the two parameters. And the variance of x is defined as mu times 1 plus phi. Sorry, 1 plus phi times mu. So in other words, you put it out, it's basically mu plus phi times mu squared, okay? And because we know this term is positive, then this guarantees that the variance is bigger than the mean. So therefore, the definition of the negative binomial guarantees that you would have overdispersion. So that's why it can be more flexible than the Poisson. And of course, based on this definition, you can see that as in the special case, that phi is 0, then this NB mu phi is reduced to Poisson phi. Poisson mu. Okay, because in this case, the variance is equal to mu, and you just reduce it. And so I'm not talking about there is actually some relationship between alpha, beta, and this mu phi, okay? Because I'm saying that if you do the integration here, then what you will left with is just alpha, beta. Lambda will be gone. It will disappear after integration. So there are some one-to-one relationship between the gamma, alpha, beta, and NB mu phi here, but I'm not going to give the actual formula because it's not very important. But what I want to say is that when intuitively, when phi is 0, it basically says that this gamma, alpha, beta reduces from a continuous distribution to a point mass. And that point mass is your lambda. So lambda is no longer random, and that's Poisson. Okay, so this is the most intuitive motivation for negative binomial for our purpose to explain the overdispersion. But I think if you take some introductory probability class, there's another formulation of the negative binomial you might have seen that is based on the coin tossing. Okay, so I'm just going to briefly mention that. And very interestingly, they gave those two motivations gave us the same distribution. So another derivation of NB. So this will be based on another set of parameterization, and that is called the, so we will need probability of success P, right? The coin toss probability. And we also need another integer R. Okay, so this is a little more specific about the formulation. So let me just put it here. So P between 0 and 1 is the success probability. Okay, and R is the number of zeros you get. So when you toss the coin, R is the number of zeros you have get. Okay, so what is the random variable here? Here, the random variable X that we call to follow MBPR is defined to be the number of ones before the R0 is seen. So this is how we formulate this problem. So in other words, we are trying to do this. This is a random number, right? So basically what it says is that, so when we do the coin tossing, say 0, 1, 0, 0, 1, 1, 0. So what it actually means is that we stop when we see the R0. We stop here and we just count how many ones are here. And this number is what we call X. So this is how we define the random variable here. And you can see by this definition, the X can range from integer 0, right? That's the minimum it can take, and up to 1, 2, and how many. So basically, this is the negative binomial formulation from coin tossing. And from this formulation, you can see that if we try to calculate the probability mass function for random variable X, taking small x value, and this small x is just, as I said, non-negative integers. Then what we are doing here is that let's do this math problem, okay? So because we know we stop at the R0, so this one is known for sure to be 0. What's unknown is the R minus 1 tosses before it, and not R minus 1, so the tosses before it. And how many tosses did we get before the R's? Actually, we know that the number of ones is our X by definition. And the number of zeros also by definition is R minus 1. right? Because we must have r minus 1 here. So this is the rth. So in total, what we have in this chain before the last rth 0 is x number of ones plus r minus 1. And we just need to decide the positions of the x ones. So it becomes x plus r minus 1 chooses x. And for each one, we have a probability p, so it's p raised to the power x. For each 0, we have probability 1 minus p. And now we need to count the last one. That's also a 0. So we have r zeros. So 1 minus p to the power r. Okay, so this is a way to derive the negative binomial. And I think this is one we can use, we can teach you in the coin tossing scenario. And in this case, when you derive the probability that random variable x takes small integer x, you don't need to do integration as we have to do in the Poisson, in the gamma Poisson hierarchical model. This is by definition, we can just derive it directly. But what's the expectation? What's the variance using this derivation? We can quickly do it. So the expectation of x, okay, so just to give everybody a quick review of this expectation, it's basically this summation, okay? So we have this x go from 0 to infinity, and we have this x times the probability mass function. This is the definition of the expectation. And we have this probability from here. So anyway, we simplify it and we can show that it's actually equal to p times r over 1 minus p. Okay, and for the variance of x, I'm going to use that very important result for calculating variance is that second moment expectation of x squared minus the square of expectation. So for the expectation of x squared, I'm going to use this formula, but by replacing small x to small x squared by small x squared. So I can do it. So I'll just give you the result. And it's actually p times r over 1 minus p squared. So if you compare these two things, you can see the overdispersion also holds for this derivation. So here the variance of x happens to be the expectation of x times 1 over 1 minus p. And so basically here we need to say one thing, right? This p, if you think about this derivation here, the p must be less than 1. So I should change this to open. Why it must be less than 1? Otherwise, if p is 1, when you toy in the cost, you will always get 1s. You will never get a 0. So therefore, you can never reach the rth 0. That will never happen. So therefore, p must be less than 1. So we don't have this dividing 0 issue. And with p less than 1, then we can clearly see that this term is larger than 1. So that's why this variance is larger than expectation, which is, again, what we expect and what we want. So basically, you can see that here, this is another case to show you that, very interestingly, so this another derivation of negative binomial also gave us the overdispersion. And under what case do we not have overdispersion? When p is 0. Okay, when p is 0, it means what? I just, very interestingly, so when p is 0, then you would have always zeros. So in this case do you still have, so in this case, when you always have zeros, can you still have x greater than 0? Actually, it doesn't seem to be the case. But anyway, so I think I will leave that. I feel like, this other derivation actually is having, I would say this is a more special case of the gamma Poisson. So this one is actually more general than this one. But this is something we can learn from the coin tossing, or easier motivation, less abstract, more concrete. So from now on, we are going to use this parameterization. So this is the one we're going to use because it's very easy to understand. So mu is the mean, phi is the dispersion parameter, and dispersion adds to the variance in this way. So it's a factor that multiplies to mean square. So the larger the phi, the larger the overdispersion. Okay, so this is something we use a lot for modeling count data. So now, assuming that we know this NB distribution, okay, now moving back to our gene expression data analysis. I think I've tried to stick with my previous notations. So this one, this is the notation we use. For gene I, let's say under condition 1, we have the count denoted as xi1 to xin. Under condition 2, let's say yi1 to yin. Okay, yin. This is what we did. Okay, so now let's say that regarding the differential expression, let's try to go from the root. How do we model it? So, we actually expect, so for gene I, maybe we can unify the notation a little bit and not talking about the, let's say, the X and Y, try to unify them. So let's say that for condition 1, okay, maybe let me do this unification. So let's say that we have this gene measured in samples 1 to n. We have n samples, okay? And each sample may belong to condition 1 or condition 2. So let me use this notation. So I drop the gene I, okay, I just say one gene. I have one gene. I drop the gene I notation. I say sample index is I from 1 to n. And I say condition index as j, which is 1 or 2. So in this case, I would basically use this notation xij, okay? And this means that the read count of the given gene, the gene I'm looking at, the given gene in sample j, sample I under condition j. So in other words, the sample index is not nested within a condition. I just number my samples regardless of the condition. I number them 1 to n. And then for each sample, we also know whether it's from condition 1 or condition 2. Okay, so that means if I number this as, so for example, if I number this as x1, xi2, okay, then xi2 means that sample I is from condition 2. So this is implied by the notation. I'm just trying to make it easy to write it this way. And also the reason I want to write this way is because later the papers I'm going to show you, they use this kind of notation. So I try to be consistent with them. Okay, so with this, then if we try to assume negative binomial, okay, so I'm looking at only one gene. So the negative binomial model, in statistics, we call this a parametric model. Parametric, the adjective means that this distribution is specified by the two parameters, and we know its closed form probability density function. So for distribution like this, so like we can write down its probability mass function or probability density function as a mathematical form in terms of its parameters. Then we call those distributions as parametric models for our data. And negative binomial is one such case. So under the negative binomial assumption, let's see how we can do the modeling. So we want to assume that the xij for this particular gene follows some negative binomial distribution to explain why the counts differ between samples and between conditions. We want to explain that. So that kind of within condition randomness, let's say the samples in condition 1, why do I have different numbers for this gene? It's going to be explained by the negative binomial. So negative binomials try to explain the randomness, and this randomness could come from biological diversity or from experimental measurement errors. They all add up together to the counts we observe. So here, we would like to have just a parameter that depends on my condition, right? So ideally, I would write this as the mu j, okay? Mu j would be the mean of this gene. Let me write here. Mu j is the mean of this gene in condition j. I need this. But this doesn't account for what I would have for the so-called batch effects, right? So you may also have some effects that makes the different samples not comparable. So that's the thing we want to correct for. So therefore, you could add another parameter that's specific to sample. And let me say that called the eta I, okay? So the eta I is the sample effect. Some may be large, some may be small. So that will change the negative binomial mean. Okay. And furthermore, we need that dispersion parameter phi, right? So then here we also have some flexibility. Do we want to assume different sample have different dispersion or not, right? We are left with that option here. So, but for simplicity, let's just forget about that. I just put a phi here without worrying about that the batch effects may affect the dispersion, not just the mean. So these, what I'm just saying here is basically all the modeling considerations we need when we model a real problem. Okay, so with this, then basically under this framework, right? If we want to test for differential expression, okay, for the DE question, then the null hypothesis is mu1 equals to mu2. Alternative is mu1 doesn't equal to mu2. So if you're going to address this question, then the problem left for you is to use data to estimate mu1 and mu2. And you are going to use mu1 hat and mu2 hat estimated from data to construct some test statistic. A test statistic. And based on what we said, we need to derive the test statistic null distribution. Okay. And finally, we get a p-value. So this is the whole framework. But you know, it's very difficult that if you don't have knowledge, you just go from mu1 hat, mu2 hat to derive a test statistic. That's too challenging. So that's why we have some classical tests you can use. So one is called the likelihood ratio test. So likelihood ratio test means that you would need to estimate mu1 hat as equal to mu2 hat as one parameter from the under the null by using maximum likelihood estimation. And you are going to estimate mu1 hat, mu1, mu2 separately as mu1 hat and mu2 hat under the alternative. So without making them the same, without adding that requirement using MLE. And then given the MLEs under the null alternative, you could write down their corresponding likelihood based on the negative binomial distribution. And then you get the ratio of the likelihood, and you know that under the null, that ratio should follow a chi-square distribution. Actually, I will make it clear. -2 times the log likelihood ratio. That statistic will follow a chi-square distribution, which is the number of the difference of the number of parameters under the null alternative. Here, the difference is 1. So it will follow chi-square 1 distribution, and that can give you the p-value. So sorry, I didn't make it very detailed, but I think the whole idea is that MLE and likelihood ratio test is the classical way of solving this type of problem. Okay, so the problem can be done using this. And for the batch effect removal, or normalization, this can also be done, under the same framework. So here you need to estimate this eta I. Okay, that's the thing you want to estimate. So let's say that we have the estimate of the eta I. How do you normalize your data? So how do you get the corrected xij from xi? So let's say the question I leave for you here is that with the estimated eta I hat, okay, how to obtain the corrected xij star from xij and from the parameter estimation. Okay, so this correction can actually be done. One way to do this is to rely on what we have seen from the quantile normalization to match the quantiles. So the idea is this. So let's say that we assume after we have the parameter estimates, okay, with all the parameters we need to estimate. So this mu j becomes mu j hat, eta I becomes eta I hat, phi becomes phi hat. So with that, let's say that we can write our observed counts xij from NB with mu j hat plus eta I hat phi hat. Okay, and you want to match it somehow with xij star, which we wanted to just from NB with the mean not depending on sample. So it's just mu j hat phi hat. Okay, that's the goal. That's what you want. And here, by matching the quantile, let me try to see what page number I need. Yeah, by matching the quantile, page number 10. So by, oh, sorry, no, 11. Oh, sorry. It should be 12. So by matching the quantile, it means that what we will do is that we will use this estimated distribution and take each value xij, find what quantile is this associated with this xij. So in other words, we put this value into this fitted distribution, get the left tail probability. And that's the probability of values less or equal than that. And then we take the same probability to this distribution and find the corresponding quantile, call that xij star. So graphically, let me just try to illustrate this. So, but this is very rough because the NB is a discrete distribution. So let's say we have 0, 1, 2, and so on. So let's say that this is the probability mass function we have for NB mu j hat plus eta I hat and phi hat. Okay, let's say this is the probability mass function. Okay, so I would say this is xij. Okay, no. Let's just say this is the probability for simplicity. So let's see that at 0, we have this probability. At 1, we have this probability, and 2, this probability, and so on. So basically, all these bars should sum up to 1. That's the key. So let's say that my xij happens to be here, okay, equals to 2. Then the probability would be just the sum of these 3 bars. Let's say that call that probability as P, okay? This is the probability. Now I go to the second NB distribution after I do the correction. So it's basically mu j hat only, phi hat here. So let's say that after the correction, by removing this eta I hat, the mean becomes smaller. Okay, so then still looking at 0, 1, 2. So it becomes smaller, then I have a higher bar 0 and a higher bar 1. maybe a lower bar too, something like that. And then I just try to match the P to the right-hand side to see where does P lie. It's possible that this bar plus this bar is less than P, but if I add those 3 bars together, it becomes larger than P. So P is somewhere in the middle. So in this case, I would just call Xij star as my new correction. Okay. Ideally, if these 2 bars add up to be exactly P, I would still call the same thing. Or if the P lies between this bar and the sum of these 2 bars, then Xij star will be called 0. So this is just the way to just translate this. If this is P, then that's how I do the correction. So hopefully this makes sense. We try to match the probability to transfer the values. And this is very similar to the quantile normalization, where we also transfer the quantile values by matching the probabilities. Okay, so the reason I talk about this is because this is exactly what the popular method ComBat has been doing. So next, we are going to look at the ComBat paper. Okay, so that's a little more complicated than what I did here, but the essence is the same. So let me go to the ComBat paper next. And after that, I will let you ask questions you might have. All right, so this is the graphical illustration of ComBat-seq. The ComBat was originally developed for microarray data normalization. It has been a very popular method ever since. And this is its new version for sequencing data. So as you can see, it uses a negative binomial model, but the model is actually a little more complicated than what we do. And I try to avoid that regression part to make it simpler for you. But basically, you see here, they put the index for gene G, while I left out the G index for simplicity. And they denote sample J from batch I. Okay, so you may consider the sample J as the okay, let me try to make a little connection. So they have this batch index. So sample J is in batch I, and batch means that these samples are measured together. Other samples are measured together. So they have this batch index, but I didn't use it in my case. I just assumed it's the sample index, and that's it. Okay, so basically here, in this case, this is their model. This is the negative binomial mean. This is the dispersion. And you can see that the batch effect is both in the mean, batch I is here, and also the dispersion. So what they try to do is that they use this regression model called the generalized linear model. So I'm going to go back to that very soon. But for now, you can just say that it's not assuming this mu is directly a linear function of batch effects and sample effects. Instead, they try to assume that's the log transform mu that follows a linear function. Okay, we'll go back to this later, but just hold this for now and see this after transformation. This intercept is specific to gene G. And they have this coefficient for the biological condition of sample J. So in our case, the biological condition is 1 or 2, means 2 conditions. And this beta G is what we call the differential expression effect, okay? Because it basically measures the expected difference between 2 biological conditions. And this is regardless of sample. It's common for all samples because this Xj is just what we call the sample J's feature or sample J's covariate. It's just taking 2 values, 1 or 2. And you can see that beta G is the difference between the 2 groups. And we have another shift offset. This is called the mean batch effect. So this is the batch I's effect on gene G. Okay, so G is here, I is here, but sample J is gone because we are not caring about particular sample. And finally, this is the total sequencing depth of sample J, the thing we talk about. It also enters this model. And actually, if you look at this relationship on a non-log scale, maybe let me try to share my paper together with this. Just give me a second. So you can, that can help me better explain it. Okay, so let me pull up this window. All right, so maybe this will be better if I share my whole screen. All right, so this is the paper. Okay, let me see. Maybe, can you see this clearly on the left-hand side? Or it's too small? Maybe let me try to change my window position like this. Okay, and then I make this 1/3. All right, so what I try to say is that, maybe make, okay. So what I try to say is that if we look at the on-log scale, then basically what's in the paper is mu Gij is equal to Nj multiplies exponential alpha G plus Xj beta G plus gamma Gi. Okay, and if I just denote this, I can factorize them. So basically I can write this times e to the alpha G times e to the Xj beta G times e to the gamma Gi. Okay, so therefore you can see that basically it's some, I will just use the common words to write it. It's sample J's size, that's the Nj, times a factor that's gene specific. Okay, gene G factor. Okay, let me make this smaller. Gene G factor times the next term is the okay, maybe I just go down, times condition effect, and finally times batch i's effect on gene G. Okay, so these are all the things together. Oh, sorry, I think I missed. It should be beta G. So this is condition effect on gene G. Okay, so altogether, it's this multiplicative effect if you don't do the log scale. So we're assuming that these things all multiply together. So it's possible that sample J is just big, so its size is large. And gene G has a lot of expression, so its factor is large. And also, we assume the conditions effect are different for different gene G. So that's why it's specific to gene G. And finally, we assume the batch i's effect is specific to gene G. So it's also specific to gene G. So therefore, you see, the first thing has nothing to do with gene G. Second is gene G specific. Third is gene G specific. Fourth is gene G specific. Okay, so we are basically explaining why the model looks like this. And for the variance term, which is this one, it's actually based on, this is nothing special, just based on the property of the negative binomial distribution. It's the mean plus dispersion times mean square. Yeah, and I already explained what they say here. So, and they will do parameter estimation. So they use the edge R, which is the DE method to estimate parameters, which I will say a little more later. So edge R uses a more, let's put it this way, uses a more complicated maximum likelihood estimation to estimate those parameters. And they also implemented the empirical Bayes I mentioned before, like the case I talked about for a t-test, that parameter, the pooled variance, that parameter. So they also use a similar idea for estimating parameters. So the reason they want to go for, that complicated empirical Bayes way to estimate parameters is because the sample sizes are small. That's the only reason. So let's assume all the parameters are estimated, right? And then how would you change your negative binomial parameter? It will be this estimated mu Gij, called mu Gij hat, minus the estimated batch effect, gamma. So because all the other things, like the gene specific factor and this, they are something correct, right? We don't need to correct those. Only the batch effect is the thing we want to remove. So that's why this method tries to remove this part by doing this simple subtraction. And also, there is a dispersion batch effect, right? Batch also affects this. So what they try to do is that they try to make this dispersion equal across batches. So let's say you have batch 1, 2, 3. I goes from 1 and 2 and 3. With the correction, you just unify the dispersion parameter to be the same for all batches. And what the authors do is to take the estimated batch effect specific to gene G for sure by averaging, and then you get this common dispersion for gene G. So I is gone. So now this is the corrected mean. This is the corrected dispersion. As a result, the negative binomial distribution, let me go down here. This is the original model. You have this mu, this phi, right, with hats as the estimates. This is the adjusted one. Okay, and what the author is saying is that basically, let's say you have this count as 12, you put it under the original negative binomial you estimated, and you look at its tail probability. Let's say the left tail, say it's 0.7. Then you go to the right negative binomial probability, you find 0.7 to the left, and then you find what's the value here, and now it becomes 8. So you put 8 into the count matrix, and that's your corrected value. So this ComBat approach can make sure that the corrected value are still integers because the negative binomial is counts. And this is different from, when we talk about the normalization by sequencing depth, by housekeeping genes, by quantile normalization. So in those approaches, it's possible that after correction, you will get non-integers. But if you want to stick with integers, you have to do some rounding. That's what you need to do. But for this case, by definition, you will still get integers. Okay, so I'm not sure if I made this clear. Do we want to ask any questions if you have?
I have a question.
Yeah.
Well, actually, so just operationally, when it takes the average dispersion factor, you're assuming that like the dispersion factor itself doesn't really vary that much over all the genes that you're testing for in your RNA-seq experiment, right?
No, because this average is not for gene. It's not across genes. It's still gene specific. It's only across the batches.
Oh, I see. Okay. Okay. Oh, I see. Okay. And then in general, though, if you're using ComBat or anything that like assumes like assumes that your sample comes from a particular distribution or a particular distribution is like a good way to model the sample. How does that affect?
Yeah.
How does that affect your choices when you're doing differential expression analysis?
Okay, I would say, so maybe if I interpret your question correctly, you're saying that this is assuming the negative binomial distribution fits the data well, right? And then you would do, I would say a natural consequence is that once you do all the parameter estimation, then this beta G hat, that estimate would allow you to do differential expression test. So because the differential expression question embedded in this model is whether beta G equals 0.
I see. Okay.
Yeah, but this is all based on this parametric model. If this model doesn't fit your data well, then the result could be useless. So I think, and I want to say that this has been a largely ignored fact or ignored concern in this field, because when you have so many or such a small sample size, let's say you have just 2 batches, and maybe a sample, each batch has 3 samples, and those 6 samples belongs to 2 conditions. In that simple setting, given such a small sample size, there's almost no way for you to verify whether negative binomial distribution fits your data well, right? Given that you only have 3 numbers per condition, how can you fit a distribution, right? So in that case, it's just a belief that, oh, NB, negative binomial, is a good model. But I think I would just try to maybe use the remaining of time to talk about another case, which is our recent work, to show that when your sample size is very big, you can observe, you can observe that the NB distribution doesn't fit it well. So in that case, you don't have to stick with those parametric models because they may not be reasonable. I hope that makes sense. And also I want to say that the negative binomial and Poisson, they have some mechanistic interpretation. So for example, if your sample is just one biological sample, you do sequencing for multiple times, then the counts you get per gene for one gene should theoretically follow a Poisson distribution because of the sampling process. That makes sense. And if you believe that, I have some additional variation to my sequencing samples before I load them to the sequencing machine, then you can say, oh, that additional variation can be fit by negative binomial. So that's why I would say negative binomial and Poisson are believed to be a good distribution to explain uncertainty due to measurement noise in sequencing machine due to the random sampling. And they're good for fitting replicates. But in some cases, your samples may not really be biological replicates. So that's where we need to be super careful about it. Okay, so maybe I think I can stop talking about the technical material here. Let me see what I want to do. Probably, okay, let's try to continue. Maybe I'll talk about that violation of negative binomial next time after we finish this. So let's say that another thing I want to show you is the DESeq2. Let me see. This is the DESeq2 paper I want to show everybody. So the DESeq2 and HR, they have very similar models. They're both based on negative binomial regression, a special case of generalized linear model. And so let's look at this DESeq2 because this method is easier to read. So basically, it starts with a count matrix with 1 row for each gene and 1 column for each sample J. Okay, so I'm trying to say that this is following from our previous discussion about gene differential expression analysis, except that in our previous discussion, if you recall, we talked about t-test. And that's basically when the sample size is small, we are assuming the data follow a normal distribution, or when the sample size is big, then the normal distribution doesn't matter that much because we have the central limit theorem. Okay, so that's the case when sample size is large, we can use t-test. But what DESeq2 is designed for, when sample size is small, then the normal assumption obviously don't hold because the data are counts. So in this case, you cannot apply the t-test. Okay, and recall we also talked about the permutation test, right? We said that doesn't assume any assumption about distribution. But when the sample size is small, we cannot permute the data for too many times. Then in that case, using the permutation test, we cannot get fine resolution p-values. So it's not working as well. So that's why DESeq2 and HR were designed to address the problem that, we have a small sample size and our data are counts, so we cannot use t-test and we cannot use permutation test. We have to use some other parametric model that can explain data better than Gaussian normal distribution. So that's the whole motivation. So let's look at the DESeq2 method. It's a count matrix is denoted by K. Note that it's a little different from our notation, with 1 row for gene I and 1 column for sample J. So basically, let me put it here. On the right-hand side, the DESeq2 setting is this K matrix okay? And the counts are Kij, and the row is gene I, okay? And the column is sample J. This is what the setting, the data is. Okay, and they try to fit a generalized linear model. This is short as GLM as follows. So basically, I'm trying to write down what the text reads here. So we assume Kij, the count, follows a negative binomial distribution with mean mu ij and dispersion they denote by alpha I. So you can see that this says the gene mean, it depends on both gene and sample. So they both determine the mean, but the dispersion is only about gene. Sample, there's no sample specific dispersion. Okay. And they also consider the mean to be factorized as this, mu ij as Sij times Qij. Okay, this, and for simplicity, they actually said that they assume this Sij, maybe I just forget about this. Look at Sj times Qij. Okay, this is better. So this Sj, you can consider this as a size factor of sample J. Okay, and this is the relative abundance of gene I in sample J. So in other words, DESeq2 is formulating its differential expression in terms of the relative abundance. So doing so, you see, by the model formulation, you can tell to use DESeq2, you don't have to normalize your sample by sequencing depth beforehand, because this model has the step to take into that sample library size into account. Okay, so then what they did is that they assumed the negative binomial model and the log linear model as part of their generalized linear model. So just put it simply, the generalized linear model is always trying to do this. Maybe let me move my paper to the right-hand side. So what does GLM do? Let me just try to say it. Okay, so for the GLM, what it does is that you have an observation, the ith observation xi, okay? Oh, sorry, maybe say yi. And also this observation has a set of covariates. So I call this covariate vector. I call that as small case xi. So sometimes this can be multivariate. So I call it p-dimensional. So it's a covariate vector, p-dimensional. So for example, let me just say that this is the ith gene, account of the ith gene. And this gene has some characteristics. For example, the length, the GC content, those kind of useful characteristics that may affect its count. Okay, so the GLM is basically saying that, let me say, I assume my yi follows some distribution with mean mu I. Okay, so by the way, yi and mu I are both scalars, so they are not vectors. And then this is what we call in the GLM as the random part. That explains the randomness in your observation. And also we have a fixed part. The fixed part is trying to link the mean, which is deterministic, fixed, to the covariate vector, which we also assume to be fixed. So therefore, the fixed part is usually in the form that you apply some function g to the mean mu I, okay, and assume that this transformed mu I is a linear function of the covariate vector. So usually we just write this as just
the intercept as alpha plus the covariant vector xi transpose times a beta vector p-dimensional. So this is the inner product between covariant vector and the coefficient vector. So that gave me a scalar. So basically this is that alpha is real and beta is p-dimensional. So this is the generalized linear model. So in other words, we allow the flexibility that is G to be nonlinear, so we can take care of more distributions besides just the normal distribution. You know, the special case of this GLM is called LM, linear model. In the linear model, in the special case, we just have yi follows normal distribution with mean mu I and some variance that doesn't depend on ith observation, common sigma square. And then we assume mu I equals to alpha plus xi transpose beta. So you see in this case, the G function is an identity function. We don't do any nonlinear transformation, and it's assumed to be a linear model with the covariant. Okay, so this is a very, very brief introduction to the GLM. And just for information, last year I taught a class specific about this called DESeq2 and the videos are actually available. So if you're interested, you can check that out. And this class, I'm not going to focus on that, but just to say this so that you understand what the essence is. And that's the essence of the DESeq2 and NB. So basically, they are assuming the counts are random with negative binomial distribution and its own mean. And then they try to say that for the mean of negative binomial, in their case, they do log transformation. So G is log. And there's some reason for that because, you know, the mean is non-negative for negative binomial, right? Negative binomial cannot allow a negative mean. So for this non-negative mean, how can you make it a linear function? Because we know the linear function can be positive and negative. So it can go down to negative infinity, go up to positive infinity, no constraint. So to achieve that, if you have a non-negative mu I, you take its log, then it becomes real value, right? After the log, you can cover the whole real line. You can cover from negative infinity to 0 to positive infinity. So therefore, the log mu I is more reasonable. It can be more reasonably modeled by a linear model. So that's just one quick way to explain why the log transformation makes sense. But theoretically, there are some more justification of why we use log for negative binomial GLM. Okay, so moving back to here, you see, with this explanation, so then in the DESeq2, you see, they are assuming this log link function, that G function, okay? And they are putting the link function on Qij instead of mu ij, because they think this Sj factor, they can deal with it separately. So they are assuming the log Qij relative abundance of gene I in sample J is equal to, you can see what they write here is this R X J R, okay, and beta IR. So what does that mean? So you can see that, let's say R, when R equals 1, okay, then XJR is XJ1 when R equals 1 is the first covariate of sample J. So what can it be? It could be, let me give you one example. It could be condition, right? It could be what condition is sample J in? That's the covariant. Then correspondingly, this beta I1, R equals 1, to be matched with XJ1 is the condition effect on gene I. Okay, so if that's the case, then this beta I1 is what we are interested in, which indicates DE. Okay, so in this case, with this formulation, then beta I1 doesn't equal to 0 is equivalent to say that gene I is DE. So that's why using GLM, you have a powerful framework to do DE analysis. You just need to include the condition as one sample covariate into the regression framework. And you can add other covariates you want to adjust for. For example, sample J's batch, you don't want that, you put in the model. So basically with the regression framework, the nice thing is that the D effect you estimate will be conditional on that other unwanted effects are removed. So you are not confounded by those covariates. Okay, so I think I will stop here and I'll come back to this next time. But I want to say that this is something not really basic because we are relying on a lot of previous like statistical terms, but hopefully I try to make it high level enough so people can still understand what's the understanding, what's the intuition behind it. But yeah, try to collect your questions and come back with your questions next time. So hopefully we can make people really understand what this DESeq2 method is doing. All right, and I'll see you next Monday. And we'll still start at 2:30 on Monday. Bye.